Hi everyone, my name is Samuel Degnan Morgenstern, and I'll be presenting with my colleagues Nick Scovran and Craig Allen. We are presenting on our senior design project, Modeling Mixing Dynamics with Stirred Batch Reactors, as sponsored by BOMAR.
BOMAR operates several reactors to produce oligomers that are used in adhesives. However, the mixing dynamics of these reactors are not well characterized and unexpectedly vary between reactors. The goal of our project was to unravel the black box of these reactors by using COMSOL, which is a computational fluid dynamics software, and obtain an understanding of the product behavior under varying process conditions.
The following chart contains the two major objectives for this project. First, we provided BOMAR with a set of Excel tables that, given a reactor, converts the input power frequency to the output RPM of the impeller. Second, we produce a set of Excel tables for each reactor that, given a product with a given viscosity and density, will outline the fluid flow behavior at different mixing speed settings. Since BOMAR provided various drawings for each reactor and impeller, a consolidated SOLIDWORKS model was produced for each reactor. These models could be imported into COMSOL for simulation and provided an easier reference than the given drawing. Seen below are some of the modeled impellers.
This flowchart shows the various steps of our project related to the COMSOL modeling. We began our study by recreating the reactor geometries in SOLIDWORKS and then importing those into COMSOL, where we added the necessary physics and fluid properties to begin the simulations. COMSOL simulates the velocity profiles by numerically solving the Navier-Stokes equations in 3 dimensions. We ran many trials of these simulations with varying fluid viscosities, densities, and differing levels of mixing intensity.
Our senior design project has two major deliverables. The first deliverable is a database for all of BOMAR's reactors to provide a mapping between the motor setting and operating choose, and the actual mixing speed within the reactor. As different reactors have different agitators, this database will enable a better understanding of the mixing parameters for a given process that takes place in multiple reactors. Furthermore, our main deliverable is the computational fluid dynamics simulations of mixing dynamics within the reactors to better characterize the mixing behavior at different mixing speeds. As shown in the figures, we can then quantitatively and qualitatively assess the flow characteristics in the reactor. Based on the understanding of the reactor dynamics, we can design future numerical experiments to optimize the mixing speed. This analysis will provide a myriad of economic benefits to this process. Your overall goal is to reduce the total cost by 5 to 10%, and this will be achieved through decreased power consumption, better quality assurance, and overall process improvements. In terms of power consumption, we know from the power draw equation that the power required for the motor is positively correlated with mixing speed. Through our analyses, we have shown how to optimize the trade-off between mixing speed and power consumption to reduce costs. Furthermore, as a result of enhanced mixing behavior, we hope to deliver a higher quality assurance to BOMAR's products. A consistent behavior will result in reduced product variability and more consistent mixing conditions between different reactors. Improved mixing will also eliminate potential problems like solidification that can freeze production by several days. Preventing these malfunctions will protect plants from hazardous safety conditions and limit the use of dangerous cleaning chemicals. Finally, our improved understanding of mixing will enable significant process improvements. Specifically, better mixing will shorten the cycle time of batches, thus allow for higher plant output. Additionally, a better understanding of mixing for a given set of fluid parameters will allow for the production of new products to be scaled up more efficiently. In summary, our mixing simulations have allowed us to provide an out-of-back characterization of the mixing process will improve the efficiency of mixing and enable more consistent product quality. These improvements will provide significant benefits in terms of reducing process and utility costs, as well as enabling better process design. As shown here, these allow for better scale-up of new processes with consistent quality between reactors. Thank you to the University of Connecticut School of Engineering, BOMAR, and the Department of Chemical and Biomolecular Engineering for the support of this project, and thank you for listening.